Section: Introduction. In this paper, we delve into the world of pre-training models that are not task-specific, a practice that has become the norm in natural language processing, NLP, due to the rise of large language models, LLMs. These models have the ability to solve complex reasoning tasks, follow instructions, and are now the driving force behind widely used AI assistants like ChatGPT. One of the key factors behind their success is their ability to improve consistently as the number of parameters, capacity, or the amount of pre-training data increases. This is remarkable for two reasons. Firstly, despite being trained with a simple objective, predicting the next word in a sentence based on its past, these models can learn complex patterns over long contexts. Secondly, this scalability is mostly observed when used with certain architectures, particularly transformers, which suggests a potential synergy between the autoregressive pre-training and this architecture. This leads us to question whether the success of scaling transformers with an autoregressive objective is exclusive to text. This is an important question, as none of the elements mentioned above are inherently specific to language modeling. Autoregressive objectives have their roots in data compression literature, and similar approaches have been explored in audio and images. The transformer architecture has also been successfully used in other domains, particularly in computer vision with the success of vision transformers, VIT. In this study, we aim to generalize the findings of LLMs by exploring if training VIT models with an autoregressive objective leads to competitive performance in terms of learning representations, with the same scaling ability as LLMs. We introduce autoregressive image models, AIM, an autoregressive approach for large-scale pre-training for visual features. We revisit previous work in autoregressive representation learning, using a modern toolset that includes vision transformers, large-scale web data collections, and recent advances in LLM pre-training. We also introduce two architectural modifications to adapt autoregressive pre-training to visual features. Firstly, we adopt a prefix attention instead of restricting the self-attention to be fully causal, as is typically the case for LLMs. This allows us to move to a fully bidirectional attention during downstream tasks. Secondly, we use a heavily parameterized token-level prediction head, inspired by the heads used in contrastive learning. We found that these modifications significantly improve the quality of the subsequent features with little overhead during training. Our AIM training is similar to the training of recent LLMs and does not rely on any stability-inducing techniques that supervised or self-supervised methods need. We studied a series of models, ranging from 600M to 7B parameters pre-trained using 2B uncurated images with permissive licenses. Our AIM models show strong scaling behavior with respect to the model size, where higher capacity models achieve better downstream performance. More importantly, there is a correlation between the value of our objective function on a validation set and the quality of the subsequent frozen features. This confirms that the autoregressive objective is adequate for the training of visual features. Furthermore, we observe consistent improvement in downstream performance as we train on more images, with no sign of saturation. These observations align with previous studies on scaling large language models. In terms of related work, while most of the literature on autoregressive models comes from language modeling or speech, few works have explored the potential of this approach for images. Some works have shown that using an architecture adapted to images, like a convolution network, significantly improved over autoregressive models built with more generic architecture, like a recurrent network. Other works have shown that scaling with more compute leads to continuous improvements. Our work follows this line of research, and we benefit from training on significantly more data, and further improvement in architecture design, training, and understanding of the scaling law. Pre-training vision models on datasets of images without supervision has been a fruitful area of research in recent years. Different approaches have been employed, focusing on various proxy tasks for feature learning. For example, some works have learned to rearrange the order of shuffled image patches, relied on clustering, or used a contrastive objective to identify each image. Most recent contrastive approaches include Dino, Bile, or iBot. Some works have proposed predictive approaches or a form of feature whitening. Other works have been inspired by BERT, where patches are masked and predicted with an autoencoder in either their discrete or pixel form. Autoregressive modeling is a form of generative modeling, and few other generative approaches have been considered to learn visual features. Some works have leveraged autoencoding, where the pretext task corresponds to some denoising task. Another line of work leverages generative adversarial networks, GANs. Most notably, Big GAN trains a large GAN and reuses the image discriminator to produce image features. More recently, DiffMay used diffusion models to learn image features. There are numerous works on scaling the pre-training of visual features with no supervision. The most notable work in this area is DINOV2, where they produce the best self-supervised features by scaling the IBOT method on a private dataset of 142M images and a 460M parameter model. However, they do not exhibit the scaling law that we observe with language modeling. They also rely on an intricate implementation of contrastive learning to avoid the pitfalls described by others. In contrast, we observe a clear benefit of scale on the quality of our features, even at a scale of a few billions of parameters and billions of images. Section Summary. The section introduces the concept of pre-training task-agnostic models, specifically in the context of natural language processing. It highlights the success of large language models, LLMs, in solving complex reasoning tasks and their ability to improve with increased capacity and pre-training data. The section then explores whether the success of scaling LLMs with an autoregressive objective is exclusive to text and investigates the performance of training vision transformers, VITs, with an autoregressive objective for visual features. The authors introduce autoregressive image models, AIM, and discuss architectural modifications that improve the quality of the features. The section concludes by presenting the results of training AIM models with varying parameters and pre-training data, showing strong scaling behavior and consistent improvement in downstream performance. Section: Pre-training dataset. We begin by training our models on a dataset known as DFN, which contains a vast collection of 12.8 billion image text pairs. This dataset has been carefully curated to remove inappropriate content, blur faces, and reduce duplication. The images and their corresponding captions are ranked based on their alignment score. From this, we've extracted a subset of 2 billion images, known as DFN2B, which represents the top 15% of samples. It's important to note that this process doesn't involve any additional curation based on the image content. Our pre-training doesn't require text, so we could use larger image collections that aren't paired with captions or have low image text alignment. We follow the common practice of oversampling high-quality data sources, so during pre-training, we sample images from DFN2B with an 80% probability and images from ImageNet-1K with a 20% probability. We refer to this dataset as DFN2B+. Our training objective is based on a standard autoregressive model applied to a sequence of image patches. In simple terms, an image is divided into a grid of non-overlapping patches, which together form a sequence of tokens. We assume that the sequence order is the same for all images. The probability of an image can be broken down as a product of patch conditional probabilities. Our training loss is defined as the negative log likelihood. Minimizing this objective over an infinite number of images is theoretically equivalent to learning the true underlying image distribution. Our training objective naturally leads to certain types of losses, each corresponding to a choice of the distribution. By default, we use a normalized pixel-level regression loss. This loss corresponds to setting the distribution as Gaussian distributions with a constant variance. We also consider a cross-entropy loss with patches converted to discrete tokens using an offline tokenizer. Our tests show that these designs work, although they do not produce as strong features as the pixel-wise loss. As the backbone, we use the Vision Transformer Architecture, VIT. For scaling in the model capacity, we follow the common practice in language modeling and prioritize expanding width rather than depth. During pre-training, we apply causal masks to the self-attention layers to model the probability of a patch given the preceding patches. This approach allows us to process the image with a single forward pass during training, without incurring additional computational overhead. However, the autoregressive objective in pre-training requires a causal mask in the self-attention operation. This differs from the standard usage of VIT models in downstream tasks, where bidirectional self-attention is employed. To address this issue, we propose to consider the initial patches of the sequence, referred to as the prefix, as a context for predicting the remaining patches. This modification helps the model to work in the absence of causal masking, allowing it to be removed during downstream adaptation. It's common practice to use certain prediction heads during pre-training, which are discarded when transferring to downstream tasks. The purpose of these heads is to prevent the trunk features from becoming too specialized in the pre-training objective, thus enhancing their suitability for downstream transfer. We opt for a simple design where we use multiple blocks of MLP on top of the final transformer layer, processing each patch independently. Pre-training large-scale models is a resource-intensive process, and even fine-tuning them is demanding. Therefore, we focus on scenarios where all model weights are fixed for downstream tasks. In this context, we only train a classification head, which reduces the risk of overfitting on small downstream datasets and significantly reduces the adaptation cost. Unlike contrastive learning, our loss is computed independently for each patch. This means that our pre-training does not incorporate any notion of global image descriptors. We find that our approach, along with other generative approaches, benefit more from an attention pooling operation placed before the linear classifier. This operation computes a global descriptor through multi-head attention pooling over the patch features, which serves as the input to the linear classifier. We refer to this as an attentive probe. Section summary. The authors pre-train their models on a dataset called DFN, which consists of 12.8 billion image text pairs filtered from Common Crawl. They use a data filtering network to rank the samples based on alignment scores between images and captions, and extract a subset of 2 billion images called DFN2B. During pre-training, they sample images from DFN2B and ImageNet-1K, and use a training objective that involves predicting image patches. They also propose a prefix transformer to address the discrepancy between autoregressive pre-training and downstream tasks, and use MLP prediction heads to enhance transferability. Section: Impact of Scaling. We've been studying how our approach scales in terms of parameters and training data. Specifically, we've been looking at whether there's a link between the pre-training objective and the performance in various benchmarks. We've also been examining how scaling affects the value of the loss function. For all these experiments, we've been using the validation set of in1K to report the value of our loss function. During training, we've been tracking the value of the pre-training loss and the classification accuracy on the validation set, based on the number of training iterations. We've noticed that both of these metrics improve throughout the entire training process. This suggests that optimizing our objective directly leads to better performance in the end. We've also observed that as we increase the capacity of our models, both the loss value and the accuracy of the task improve. This is consistent with what we've seen in language learning models, LLMs, and can be directly attributed to the optimization of our objective function, which in turn leads to stronger representations being learned. We've been tracking the progression of the validation loss as we pre-train on either a small dataset of 1 million images, in 1K, or a larger set of 2 billion images, DFN2B+. As expected, training on in 1K quickly leads to a low validation loss. However, this loss worsens at the end of the training, indicating overfitting to the training data. When training on the uncurated DFN2B dataset, the model starts with a higher validation loss, but the loss continues to decrease with no sign of overfitting. When we add a small amount of in 1K data to the same dataset, we see further improvement in performance that eventually surpasses pre-training on in 1K. We've confirmed that the resulting model also leads to better performance in the end. We've also been studying the impact of extending the length of our pre-training schedule. We've found that models pre-trained with a longer schedule achieve significantly lower validation loss. This suggests that one can improve the performance of our approach either by increasing the model capacity or by pre-training for longer schedules. Interestingly, we found that lower capacity models trained for a longer schedule achieve comparable validation loss to higher capacity models trained for a shorter schedule while using a similar amount of computational resources. This finding is consistent with previous studies and suggests that our approach could follow similar scaling laws. However, we'll leave further investigations in this aspect for future work. In this section, we've been investigating the impact of some variations in our model and training objective. These ablations are conducted using an AIM 0.6b model, which has been pre-trained and evaluated on the IN1K dataset. The results of these ablations are presented in a table. We've been exploring various potential representations for the target patches. One approach is to use the raw pixel values and train the model with mean squared error, MSE, regression loss. Another option, proposed by previous studies, involves using per-patch normalized pixel values instead of the raw signal with the same MSE loss. Finally, another option is to use a discretized representation of the patches, either using k-means or a discrete VAE. In this case, the model is trained using a cross-entropy objective similar to language modeling. Our experiments show that our approach performs best when using the MSE objective with normalized pixel values. Autoregressive pre-training typically follows a specific order of traversal to facilitate the prediction of the next token. In the case of language, the traversal pattern is clear, as text is read and written one word at a time in a sequential manner. However, for images, determining the traversal pattern is less obvious. We've been exploring various deterministic patterns, including raster, spiraling out, checkerboard, and randomly pre-sampled patterns. Detailed examples of each pattern are found in the appendix. Even though our model performs reasonably well with each pattern, we've observed that the raster pattern leads to significantly higher performance. We've been exploring the impact of the information content of each patch by adjusting the lower bound of the cropping scale. On one hand, opting for a cropping scale that is too small leads to an easier next patch prediction task as neighboring patches' similarity increases. On the other hand, using a large cropping scale can lead to severe overfitting unless the dataset size is sufficiently large. Since this study is conducted using IN1K, we've observed a clear drop in performance due to overfitting. We've been measuring the impact of incorporating prefix attention during pre-training, as opposed to using standard causal attention. We've observed that pre-training with causal self-attention produces models that are effective in downstream transfer tasks only when the causal mask is preserved. These models experience a significant decline in performance when bidirectional attention is employed. However, pre-training with prefix attention leads to models that operate effectively in both causal and bidirectional modes. Notably, the best performance is achieved when combining prefix attention during pre-training with bidirectional attention during downstream adaptation. We've considered different types of heads on top of the backbone to make predictions at the pixel level. Using no heads performs reasonably well, but adding an MLP further improves the quality of the backbone. Interestingly, replacing the MLP with a full-fledged transformer of the same depth and width only yields a marginal performance improvement but at a significantly higher computational cost. Therefore, we've chosen to use an MLP head in our approach. We hypothesize that these heads specialize in capturing the low-level signals necessary for accurate pixel-level prediction. By incorporating a head, the trunk can learn higher-level features that are more suitable for downstream transfer. We've presented the design specifications of our approach in a table, outlining its width and depth. Unlike the original design of VIT, where the depth is scaled more rapidly than the width, we've adopted a scaling strategy similar to that of Llama. This allows us to scale our model more gracefully while maintaining a reasonable depth. We've validated the effectiveness of a wider architecture in a table. Our findings indicate that even for the relatively small-scale AIM 0.6b model, a wider architecture not only delivers strong performance but also improves training stability. This observation supports the notion that some of the insights gained from training LLMs can be similarly applied to other domains. For all ablations, we report the linear and attentive probing results. We've observed that, consistently across all experiments, attentive pooling provides a significant boost to performance as it allows for a more nuanced aggregation of local features, circumventing one of the main weaknesses of generative pre-training: the absence of an image-level global descriptor. The MLP plays an important role as ablated in a table. In another table, we've further investigated the capacity of the MLP head and how it impacts downstream performance. We've varied the capacity of the head by either changing the number of MLP blocks or their width. By default, we use a head of 12 blocks and an embedding dimension of 2048. First, we've observed that increasing the capacity of the MLP either through depth or width leads to consistent improvement in the downstream performance. Second, we found that increasing the number of MLP blocks with a fixed width leads to a larger improvement compared to increasing the width for a fixed depth. Interestingly, we could not find a point where increasing the MLP capacity failed to yield further improvements. We did not explore higher capacities beyond those reported in a table, as it would lead to models with disproportionate head and trunk capacity. Section summary. When scaling our approach in terms of parameters and training data, we observe that increasing the model capacity and pre-training for longer schedules result in improved performance. We also find that using the MSE objective with normalized pixel values and the raster pattern for autoregressive pre-training lead to the best performance. Additionally, incorporating prefix attention during pre-training and using an MLP head on top of the backbone further enhance the quality of the model. Section: Pre-training objective. We've been comparing our architecture, which is trained with an autoregressive objective, to the masking objective that's commonly used in language by BERT and in vision by Bate and May. It's important to clarify that we applied the masking objective in the same context as our autoregressive image models, AIM, so we could focus on how the pre-training objective impacts performance, separate from other design differences between AIM and other methods. In the masking baseline, we randomly selected masks and replaced the masked patches with learnable mask tokens. Our findings show that AIM performs better with an autoregressive objective than a masking objective, which aligns with previous reports and further supports that our improvements come from using an autoregressive objective. We also compared AIM's attentive probing performance to other top-tier methods across 15 diverse benchmarks. When it comes to generative methods, AIM holds its own. It significantly outperforms Bate and even AIM 0.6b, which has the same capacity as May-H, performs better on average across all benchmarks. We also compared AIM to the May-2b model, which was pre-trained on a private dataset of 3 billion images from Instagram. Both AIM-3b and AIM-7b outperformed MAE-2b, with AIM-7b showing a particularly large improvement. It's worth noting that, like AIM, two other generative approaches, Bate and MAE, also benefit from attentive probing, which helps to close the gap between generative and joint embedding methods. In terms of joint embedding methods, AIM competes well with methods like Dino, ibot, and DINOv2. On average, AIM outperforms Dino and ibot across all benchmarks, but falls short of DINOv2, which uses higher resolution inputs to achieve its results. However, AIM achieves this competitive performance using higher capacity trunks. Plus, AIM's pre-training is much simpler and can be easily scaled in terms of parameters and data, leading to consistent improvements. On the other hand, top joint embedding methods like DINOv2 rely heavily on a number of tricks to achieve strong performance. We've noticed that higher quality features can be extracted from shallower layers compared to the features from the last layer. This is likely due to the generative nature of the pre-training objective, which is inherently different from the discriminative downstream tasks. Therefore, the features with the highest semantic content don't necessarily concentrate around the last layer. We also looked at low-rank adaptation, LoRa, a popular and efficient fine-tuning method. We found that LoRa works well with AIM, leading to a significant boost in performance compared to frozen trunk evaluation. For instance, AIM-7B improves by 3.9% compared to the last layer's performance, while fine-tuning only 0.1% of the trunk parameters. In this paper, we've presented a simple and scalable method for pre-training vision models at scale without supervision. We used a generative autoregressive objective during pre-training and proposed several technical contributions to better adapt it for downstream transfer. As a result, we observed several desirable properties for our autoregressive image models. First, we can easily scale our models to 7 billion parameters using a basic transformer implementation, without needing stability-inducing techniques or extensive adjustments of hyperparameters for each model scale. Second, AIM's performance on the pre-training task strongly correlates with downstream performance. Third, AIM achieves strong performance across 15 recognition benchmarks, outperforming previous top methods like MAE and significantly closing the gap between generative and joint embedding pre-training approaches. Finally, we didn't see any clear signs of saturation as we scaled either in terms of parameters or data, suggesting that there's potential for further performance improvements with larger models trained for even longer schedules. We hope that AIM serves as a starting point for future research in scalable vision models that effectively use uncurated datasets without any bias towards object-centric images or strong dependence on captions. Section summary. The authors compared their architecture, trained with an autoregressive objective, to the popular masking objective used by BERT, BAIT, and MAE. They found that their approach, AIM, performed better with an autoregressive objective, providing further evidence that their improvements stem from the utilization of this objective. AIM also outperformed other generative and joint embedding methods, demonstrating its scalability and potential for further performance improvements. In addition, the authors observed that higher quality features can be extracted from shallower layers compared to the last layer's features, likely due to the generative nature of the pre-training objective. They also found that low-rank adaptation, LoRa, led to a large boost in performance for AIM, demonstrating its compatibility with this efficient fine-tuning method. Overall, AIM is a simple and scalable method for pre-training vision models without supervision, achieving strong performance across multiple recognition benchmarks and narrowing the gap between generative and joint embedding pre-training approaches. The authors believe that AIM can serve as a seed for future research in scalable vision models that leverage uncurated datasets without bias or dependence on captions. Section. Limitations. While our method, AIM, shines in its ability to scale smoothly and efficiently handle large amounts of unsorted image data, it's important to note that other techniques may offer different advantages. For instance, the MAE method is highly efficient in terms of sample usage and can learn effective representations with a minimal amount of pre-training data. This reduces the likelihood of overfitting, a risk that our approach might face. Contrastive methods, on the other hand, currently yield more robust representations for a given model size compared to generative methods like MAE and AIM. However, they present substantial hurdles in terms of scalability and the manageability of loss due to the complexity of their objectives. We'd like to express our gratitude to Brandon McKinsey, Samira Abner, Preetam Nakaran, and Jiatao Gu for their invaluable feedback throughout the project. We're also grateful to Edouard Grave and Hervé Jegu for their stimulating discussions during the project's early stages. Our thanks also go to Marco Cuttori, James Thornton, Pierre Ablin, and Eugene Njai for their support and for the many productive discussions throughout the project. Lastly, we extend our appreciation to the entire machine learning research team at Apple for their helpful discussions and assistance with infrastructure and data.